Okay, let's get started. We continue our lectures on data science for business, and the topic of today's lecture is time series forecasting. So the topic of time series forecasting is important for very many industries. And here is just a few examples. If you think about logistics and transportation, it's really about forecasting the schedule of the arrival of the goods, for example, in order to satisfy customers and in order to prepare the workforce and plan the workforce or delivery mechanisms. Obviously, forecasting in sales volumes is absolutely critical for any retail. And over there, we're trying to predict both demand and possible sales. If you take on insurance industry, there also there is a need for forecasting to calculate, to predict the amount of both claims and participants of insurance. Clearly, within manufacturing, you want to predict potential malfunction of equipment or predict the output, the yield of the processes, or like with energy, try to predict and plan the demand for energy and plan production plans for energy. And that's just a very, very small sample of the reasons why you want to do demand forecasting, or time series forecasting. Now, when we, today, as in this lecture, in this course, we'll mostly focus on retail, and so we'll be focusing on forecasting for demand and forecasting for sales volume. Okay. So when we see retail sales data, it actually looks the way it is shown here on this picture, which is quite spiky. And here we're just showing for the sales, the volumes of sales for different potential items. And typically within the sales forecast, what we would like to do is to try to use past sales and sales measured as transactions data through transactions data. So we want from past transactions predict the future sales. So why do we want to do it? Well, because in order to provide those sales, we need to obviously stock the items for sale, right? And depending on the sales volumes and expected sales, you need to pretty much align the entire supply chain, right? From the purchasing, from orders, purchasing, through delivery, to like workforce and placement on the shelf of the store. And this all sort of mechanisms, this entire value chain is being driven by prediction of the demand and the predictions, the forecast of the sales. So how to like estimation how much of different units we're going to sell. And whenever we're talking about sales volume, it can be computed by the category of the product, or sometimes even by particular SKUs. So sort of demand forecasting is a process of predicting what demand would be on certain products in the future. Now, demand forecast and sales forecast are actually slightly different things. And in fact, if you look at the sales history, it does not always reflect the demand, because you might end up having an empty stock, and the demand will be there, but there were no items, and so the sales do not actually reflect the demand. Sales will be less than demand. Or you can also think about situations when there are some promotions were happening, and then demand, then the demand obviously depends on the price of the item, right? And so with the different pricing, demand would change. So as we just talked about, demand forecasting also needed across multiple parts of the supply chain, from customer relationship management to logistics to marketing to manufacturing of the goods. Now notice here we have like two different curves. One of them shows the sales and one of them shows demand forecast, and they're not always the same, but very often retailers really want day level forecast for effective replenishment of products, especially if we're talking about fast moving consumer goods, the food items, or if we talk about restaurants. So over there, you actually want daily forecast that will take into account not only sort of average demand, but sort of up to the weather information. So you might notice that a lot of things might affect demands, right? Like price changes, promotions, and various other business decisions will actually change the demand, right? And so though today in the homework and in the discussion later, we'll be looking at sort of vanilla type or like academic type of exercises. When it gets to the real business problems, there are a lot of factors, there are a lot of external factors that will affect your forecast. So demand forecast is one of the sort of is based on a time series forecasting, right? And what's time series? Well, everything that is observed sequentially over time, is a time series, every variable. And forecasting time series is pretty much trying to predict, so it's a prediction problem, how the sequence of observations that we had will continue into the future. And so in this picture, you see, the sales, for example, and I want to forecast how it will go forward. So when we do those forecasts, there are a couple of things we take into account. Well, that the numerical information about the past is available. And then we're also assuming that the past patterns will continue into the future. But again, remember that in real life, you might also need to control for or calculate the dependency on external factors. There are some very unique challenges that are characteristic to the time series forecast, comparing to other machine learning scenarios. So first of all, forecasts are often required at multiple time horizons, which means you want to have a forecast, in a day, in 3 days, in a month. So you might sort of need to calculate different sort of deltas into the future. The other important point that compared to traditional machine learning, the data points that you have in the time series data is usually very highly correlated in time, which means, let's say if we're talking about demand or supply, the tomorrow value actually depends on the today's value, and today's value depends on the yesterday's value. So, next second depends on the current second and the previous second. When you look at traditional machine learning, usually data points, separate data points, are considered to be, or are thought of being independent and identically distributed. When we talk about time series, there is a correlation between data points. Now, there are some global patterns that often occur in this data, but each literally time series will be very different. You might notice periodic patterns, and it's called usually seasonality, especially when we talk about the demand or supply calculations. And seasonality includes like literally seasons, right? But also we can talk about monthly changes or weekly changes. Sort of weekends look similar to each other, and then they repeat like every 7 days. And then also quite often very different times, very different length of time series available for calculations, right? So these things are quite unique again to time series modeling versus traditional modeling. Some factors to have in mind, that literally each time series, though, it looks like time series, right? But it has kind of been generated by a very different underlying physical process. And if you think about like sound wave versus, I don't know, electricity versus demand, these are very, very different physical, or stock price, very different physical processes, very different processes that generate those time series. And so though they're all time series, they'll be very different. And some methods that work for one time series will not necessarily work for another time series. As I mentioned before, there might be correlation within the data points, but also if you have multivariate data, which is you have multiple time series, then covariates will also play an important role. If you're thinking about multiple, for example, not thinking about demand forecasts, but say working with multiple sensors data and sensors that measures the same process. And also, since it's forecast and looking into the future, it is very helpful to have a uncertainty estimation, right? To actually not provide just a sales volume, but say, the interval, right? Where you expect your actual result would be. I mean, every calculations carries an error. And when we're thinking about, time-dependent variables, when we think about, forecasting, we want it's very helpful to actually provide an interval, right, which you can actually trust rather than single value as a result. Okay, so what methods are available for time series forecasting? Well, there are some very, very classical methods that are literally based on the fact that the data points within the time series are very much correlated. In fact, quite often, the best predictor for the next value is a previous value, right? So, and quite often this is used as a baseline. If you want to predict the next, the value in the next moment of time, you just take the value in the previous moment of time. So, but if you want it to be, of course, more precise, you want to do better than that, but still using this autocorrelation property. Autocorrelation means, the values at t+1 correlated with values at time t -1, etc., etc. So if we want to just build univariate model, we can just write it as a function, yt+1 is a function of variable, the same variable at the time t -1, t-2, as much as we want to. And then the goal of the modeling would be to find the function f. And you can actually even think about like very simple linear regression, which is done within the window, and that's usually called moving average. Or you can come up with different functions that puts different weights on time steps, closer to you or further away, and that's called exponential smoothing, or very famous method ARIMA. We're going to talk about it a little bit, but all of those methods have exactly the same idea. They're all based on the fact that within the time series, data points, consecutive data points are correlated. And so you can use previous data points to predict the value of the next one. On top of it, of course, you can also introduce some external factors and external variables. But then we can also look into into the problem of time series forecasting more as a machine learning method. And then we can, in fact, try to build a machine learning function that will connect the value of our time series on with some factors that also changing with time, and determine the function that connects it. Or we can also add, for example, some dependency on a so-called autocorrelation dependency, right? So the values of time t plus h, depending on the value of the same variable y at some previous moments of time. And correlating the problem that way, we can then use pretty much standard machine learning methods to solve it. Now, there are a couple of things which is important, which makes a difference compared to sort of non-time dependent modeling, is that the order of observations here matters, right? You cannot just randomly permute observations. That is very important here. I'm not putting here like sort of the state-of-the-art methods, which are methods based on the deep learning, and today is even on transformers. But that's something that people currently use a lot for time-dependent data, if you have a lot of that data. So it is actually, though algorithm can be quite powerful, it is helpful to do some sort of magic tricks, some pre-processing of the data before sending it through the algorithm, right? And one thing is, looking at the trend, and so detrending the data. So for example, if we notice that, so for example, there is a trend like increasing value, constantly increasing value trend, then we can probably remove that increase, right? And just sort of factor it out. And that will make, that will make work easier for our algorithms. Or for example, if there is a seasonality, which is again regular short-term variations, then we can try to take that into account literally sort of by hand, right? Various cycles, you can also extract them, and removing that from the data will leave us with a residual, and then we'll be modeling residuals, which actually can be easier compared to the modeling sort of the entire time series. So here is an examples where you see that on the blue line there is overall data, say sales data of a period of some period, and you notice that there is a increasing trend here, and you can actually take an average and get that sort of red line. That will be the trend. You can have this linear trend, and you can actually subtract that linear trend and then just work with that residual, because that linear trend is obvious. And then, to do the actual predictions, you will add back that linear trend because you're believing that's not going to change. Or if we look at the seasonality, you can also, instead of modeling this week 1, week 2, 3, and 4 separately, you can actually think about them as a sort of you're modeling 1 week interval only. So this is a decomposition. That's what decomposition looks like. You actually start with this observed variable. Then you, for example, estimating the trend through sort of rolling mean, which is you just sliding a window and taking a mean of that window. You can actually make it smaller or larger. You can actually think of like, trying to calculate a linear trend if you want with a sort of least square map for the straight line, or you can just estimate a trend by this rolling window, and then you can subtract that trend, and then you get a sort of detrended signal, and then you can in fact remove, if there is a periodic component, you can actually remove that periodicity again, having computed it. And what's left is this difference in between your trend, periodic signal, and some small fluctuations. And those fluctuations can be noise, or can be quite meaningful. And depending on the problem you're dealing with, you might actually as well try to model those fluctuations, right? And then the original signal will be reconstructed by adding together the trend, the seasonal component, and then those additional fluctuations. So there are several ways of doing this. One way is, in fact, you can just think about this as a summation, or alternatively, you can actually try to factor it as a product. Both of those approaches are known and sort of being used. Again, you might want to try to model the data as is, and sometimes it works pretty well. But if it doesn't, then what you do is you try to do this decomposition and then model the residual. Now, something also to observe is that, as we discussed, there is a quite strong correlation, or correlation linear, which is a linear relationship in between the future values and the previous values. And when we talk about time series, we usually talk about autocorrelation, which means the value of the y at time t depends on the y at previous moments of time. And so here you see the picture of on the left hand side, there is a picture of the passenger count or air passengers as a function of time, and on the right hand side we actually take a lag of 1 year and just measure plot the number of passengers previous year towards next year, and you realize that there is like really strong trend in terms of how the number of passengers next year depends on the number of passengers in the previous year, right? Now, of course, things are diverging, so probably you don't want to calculate sort of one number and then add every year that number will change, but you notice that there is a clear dependence next year from previous year. So within this classical time series analysis, what do we do? Well, as we discussed, we can actually can decompose using this sort of trend to cycle to seasonality, and then try to say that the prediction, the value of t plus h will be sort of dependent on the period, and we can take the value from the previous cycle, right? And that will be the prediction for the next value. But then there are sort of better methods. Some of them are called, one method is called exponential smoothing, where we're not just taking the previous observations, but we're taking them with different weights. If we, of course, we can remove, for example, some trivial seasonality, but then we'll consider value y hat at t plus 1, right, as a combination of y at time t, and then at t minus 1, but with some coefficient, and here it's alpha times 1 minus alpha, and at t minus 2 alpha 1 minus alpha squared, etc., etc. And so it's called exponential simply because when you combine those weights, it's sort of decaying exponent. More interesting, more powerful method, and actually very well known in statistics method and econometrics, is ARIMA, which is autoregressive, right? Again, autoregressive means you're predicting the future values from past values of the same variable. Integrated moving average. Moving average means you have a sliding window that you move through the data. And it's actually a class of various methods that work with this regression type of approach. And you notice that in this type of methods, you do have coefficients, and you can actually compute those coefficients to create a better prediction. Now, a couple other important points about a classical time series analysis. Now, it works well when the data is stationary. Now, stationary data mean the properties does not depend, the property of the data doesn't depend on the time, on the interval in which you do the measurements or do the observations. For example, for stock prices, it's really not true. The value, the properties might change like literally daily or hourly. But typically for the stationary data, values like oscillate around the mean, and that kind of the mean stays constant during the time. And the variance, which is the scale of fluctuation, also remain pretty much constant. And so, and you also remove like periodic stuff. And so, when you see this, like the data on the left, that is a stationary data. And on the right-hand side, there are examples of non-stationarity where you see like large oscillations, or maybe there is a trend. Now, we already talked about this, that you can in fact do the trending or remove seasonality, and that will bring your non-stationary data to stationary, and you want to model stationary data. And that's what's typically done. One other way of doing this like very, very simple way and extremely widely used is called differencing, which is you literally, compute the difference between consecutive observations. And then you model not the original signal, but this delta, the difference. After you model the difference, you can actually reconstruct the original signal by literally, starting with just adding it, the original signal at some moment of time, and then adding delta will actually create your signal at the next moment of time. So that's probably the most widely used method of dealing with non-stationary time series is, using differencing before you actually run machine learning algorithms on it. So we have discussed classical methods. Now let's take a look at forecasting with machine learning methods. So traditionally, when we set up machine learning problem, we have say target variable y, and then the sort of independent variable x. We might have like multiple variables, multiple factors, but let's say they all depend at some, they might depend on time. And so typically with machine learning, we can do like, direct modeling, which is we predict the value of y at time t as a function of value of x, x1, x2, x3, etc. at time t, and maybe some x's some factors that do not depend on time. But that's not a forecasting, right? This is something where we, in every time moment, we predict the value based on the measured factors at the same moment of time. When we talk about forecasting, we want to look into the future, right? And so that means modeling with a time lag. And the way to do this is to think about both y and x, sort of instead of factors, we actually put in also value of y, right? Because remember, the time series usually strongly autocorrelated. And so what you do is you actually introduce the values, the values of the target variable, the values of y itself, as a factor in our model. But the value of y at time t will be used to predict the value of y at time t plus h, right? And that's your sort of step of prediction. And so you're actually building a regression that is y at t plus h as a function of y of t, right? So you're using previous time steps as input variables and to use next time step as an output variable, right? So if you actually take the table sort of, you have the values of y, then what you do is you just shift it, say by some step h, and here it's just shifted by one value, and then use it as also the factors. And you can just literally build a regression based on that. Now, if of course you have on top of it, you have more variables like, x, not only y, but also x's, well, you actually, then you add that to your regression. So then the function y at t plus h will be a combination of function of y at time t, and then also, all other variables, x1, x2, x3, etc., and also constant factors. And then that's really creates a regression that generates for you a forecast. Now, when you do this, first of all, we're predicting into the future, right? We're predicting onto some next time steps. And the prediction is done within the prediction window. We can either predict one variable, we can predict average variable for this window, or we can predict sort of one value at the end, at the beginning of the window. And this window will be sliding, right? And when you're sliding the window, you literally create for each position of the window, you have a y variable and you have x values, and that creates for you a row in your matrix that you're going to use within the regression modeling. And then you take this window and you slide it through your entire data set. So additional parameter will be how far you slide the window. you can potentially just do it like sort of one-time step or several time steps. And so you have, you know, the look ahead window, sort of how much steps ahead you want to predict the value. You have a look back window, that's where you actually pick up your values of both signal and all your parameters, right? And then based on that, you build your regression model, but this regression model will be sort of a single model for all the positions of this window. So this window slides through the time axis, right? And that will create for you the model matrix. Now, compared to traditional machine learning, there is one thing to keep in mind, is that here, when we do training, testing, validation sets, we have to be very, very careful in terms of time, right? So simple cross-validation is not going to work, because you do want to preserve here the time sequence. You want to avoid what's called signal leakage, which is your test data, of course, should always follow your training data and shouldn't be sort of intermixed. And that's what usually happens with cross-validation. Now, there are ways to do cross-validation for time-dependent data. You might actually talk about it in a seminar. But the key is, to make sure whatever you predict is in the future compared to the data on which you are training. So, and sometimes you even want to have a gap, some sort of small time gap, in order to make sure you do not run into some sort of dependencies that will propagate from the future into the past. And in terms of the metrics that you want to use, it is the same metrics, the standard metric that we use for any other methods, for regression methods, which is mean absolute errors, mean squared error, RMSE, or R squared. That remains standard. Okay. And so that was a very quick introduction into forecasting, time series forecasting. It's really quite a big subject because there are a lot of very, very specialized methods. Now, we talked today about like a few classical methods like exponential smoothing, moving average, or ARIMA, and also touched upon how we can use machine learning algorithm, how you can convert forecasting problem into sort of traditional machine learning problem. Now, if you want to go deeper into this topic, I would recommend you looking into deep learning applications. And here is also a book, how you can use deep learning for time series forecasting. That's sort of the use of deep learning today is the state of the art within the field. And with that, we are done with the lecture. Any questions?
Thank you. No questions.
If there's no questions, then thank you. And we're going to have a seminar soon. Bye now.
Bye.